So for those of you who don't know me, I'm Frank Eparvier. I'm a hardware weenie. I make instruments that measure the solar EUV. And as Rodney said, it's very difficult. Okay, I will talk about the solar EUV irradiance and measurements of it, and concentrate primarily on the time C and SDO EVE data, as they give the best spectral and temporal resolution to the EUV. And I'll talk about new insights that we've learned from SDO EVE and what the future is for EUV observations. This is the solar spectrum from X-rays out to the infrared. And everybody, the blue line is the spectrum. Everybody recognizes the black body radiation through the visible. What we're talking about is just this wavelength range down at the short end. That's a very important wavelength range, one, because each photon packs a huge wallop. The energy in a photon goes as 1 over the wavelength. So these photons are imparting a lot of energy into the Earth's atmosphere. And as this red line shows, the amount of variability in the visible is very small. But at the short wavelengths, it can be huge, several orders of magnitude on all different timescales. Here is a graphic where I've tried to capture all of the measurements of the EUV and FUV. So on the vertical scale, we have wavelength from 0 to 200 nanometers. The EUV is usually just considered this bottom half. And on the horizontal scale is time from 1960 to 2020. You can see that we have quite good coverage in the FUV, but very sporadic coverage in the EUV. And even though there are big boxes for some of these, like the SOLRAD and AEE and SOHO, these instruments have different limitations of time cadence. Some of them are only daily measurements. Some of them are limited in wavelength resolution. Some are broadband. Some are just certain sections of the spectrum. It really wasn't until till timed that we had a full spectrum measured in the EUV at a reasonable time cadence. And now with SDO and the future with GOES, we'll have that covered even better. But there's always been problems with accuracy, precision, cadence, wavelength resolution, and just time coverage. The old proverb about give a person a watch, they know what time it is. Give them 2 watches, they have no idea what time it is. Make 2 measurements of the solar EUV, and they disagree. And so there's been lots of disagreement, especially at the short wavelengths throughout these years, because there were only sporadic measurements. And we think we've resolved some of them from factors of 4 down to maybe factors of 50% discrepancies. The solar EUV consists of emission lines and continua that are coming from different parts of the solar atmosphere and coming from plasma at different temperatures. And that's what makes it so complicated. There are some lines in here that are coming from the chromosphere, which is, say, 6 to 10,000 Kelvin. Other lines are coming from the transition region, which is from 15 to maybe 1 million Kelvin. And then the corona, which can be up to a couple million Kelvin. And all of this is very variable on the sun, depending on solar activity, magnetic activity. And so each of these regions in temperature in the atmosphere of the sun varies differently from each other. And so different lines in the solar spectrum scattered throughout will vary differently with time. Irradiance, as we've already alluded to, varies on all timescales. You have the 11-year solar sunspot cycle, which is also seen in the EUV. You get solar rotation, the beacon effect, where active regions, which are dark in the visible, are very bright in the EUV and X-rays, and they act like a lighthouse as the sun rotates, and you get a modulation on a 27-day cycle. And you also get flares, which last from seconds to hours. And certain wavelength regions in the solar spectrum will change by several orders of magnitude over minutes. Let's move to measurements. The timed mission was launched in late 2001, started operating in 2002, and it measures the full spectrum from about 27 nanometers up to 195 nanometers at 4 angstrom resolution. But it's only measuring every 96 minutes. It measures for 3 minutes every 96 minutes. It's a low Earth orbiting satellite, so it's not staring at the sun. Shortward of that, in this important range that Phil pointed out is important to photoelectrons, C actually only has a few broadband measurements, photometer measurements. And so our data product, we put out a data product that's all the way across this as a spectrum, but our data product, shortward of 27 nanometers, is a model based on scaling the broadband measurements. And if you want C data, go to the website. So what did C give us? C gave us a data set from roughly solar maximum in 2002, a little bit on the downward side, through the solar minimum and continuing to the present. And I've just plotted up 3 1-nanometer bins showing that we're capturing the solar cycle variation, the solar rotational variation, and the C mission was designed to measure a daily EUV. We do measure every orbit, every 96 minutes, but the instrument was designed to average those up and get a daily irradiance. Another thing we learned, and this is very similar to a plot that Rodney showed, is the amount of variability at different timescales is different at different wavelengths. So this plot is showing the amount of variability versus wavelength for different timescales. So the black is solar cycle, and you can see how the spectrum varies most over a solar cycle at the shorter wavelengths. The red is the solar rotation. It has a very similar shape to the solar cycle changes, but it's much lower because it's just one active region or a collection of active regions moving around. The blue and green are from a flare. This is a particularly large flare, an X2 flare, but it shows that even within a flare, the variability is different at different wavelengths over the short period of time. The blue is showing the impulsive phase of a flare, and this particular flare was peaking here in the about 70 to 80 nanometer range, and the longer, slower, gradual phase is the green, and it has a different variation through it, wavelength. So what we didn't know from C was we didn't understand very much the short wavelength spectral variability. Like I said, we had to use a model, and that model was just really guesswork based on our broadband measurements. We also, because of C's low time cadence of 96 minute measurements, only caught a few flares, maybe 3 or 4 dozen flares so far, and only caught them every 96 minutes. So we biased towards long-term flares as opposed to short-term flares and things like that. So we didn't have a very good understanding of how the sun varied with short time scales. So then we designed SDO-EVE. And SDO-EVE was designed to measure just the EUV, and all of these different colors and bands are different instruments on EVE, different channels, because it's very difficult to measure this large wavelength range technologically. Each different wavelength range has its own problems, so you design different instruments to measure different wavelength ranges. But the primary instrument on EVE we call MEGS, a multiple EUV grading spectrograph. It's also 3 channels, but it's covering 1 angstrom resolution from about 6 nanometers up to 105 nanometers at 10-second time cadence. So every 10 seconds, we get a full spectrum. We also have some broadband measurements at other wavelength ranges. And the data products are coming out. We give out a daily average and 10-second spectra at 1 angstrom and 1 nanometer resolution from early May 2010 to the present. We also have all our broadband data. at higher time cadence. The broadband instruments are measuring quarter second. We also, to address Rodney's need and other people's needs for real-time data, SDO is in geosynchronous orbit, and we're sending data down in real time. And we process it, and we're getting out a space weather data product within usually about a minute to a minute and a half. And those are the bands, and we just released with version 3 a crudely calibrated spectrum that comes out every 3 minutes, or with a 3-minute latency. It's coming out every minute is the time cadence of the data. So some of the things, the new things we learned with EVE are that the quiet sun is not quiet. These are 3 panels of different wavelength ranges, 0 to 7 nanometers, 33.5, and 17.1. These 3 wavelength ranges come from different parts of the solar atmosphere, and they vary differently. This is from the first week of May. Each one of these vertical lines denotes a day boundary. During this period, right in here, the GOES X-ray measurements were down in the noise. This was quiet. You'd say there were nothing happening on the sun. There were no numbered active regions, nothing really going on. There were a few ephemeral regions. But if you look at the EUV, at these 2 wavelength ranges, you see lots of variability. On daily, across a day, there's changes. Even sub-daily, there are 5 to 10% fluctuations going on in the UV. And this is not instrumental. This is going on the sun. And if you look carefully, you'll see that the phasing of these fluctuations are different. They're not all at the same time. And that's because there are spots on the sun that are heating up and cooling off. And the emission lines increase and decrease on that heating and cooling. And so a daily proxy is not capturing any of this variability on the sun, which can be 5 or 10% changes going on across the EUV. And one number is not going to capture differences between wavelengths where things are not in phase at all. EVE is also continuing the C long-term data set. Black is C and red is EVE, and I've plotted it with for 2 different wavelength bins here. They're different origins on the sun. This includes 304, and this includes the 33.5 nanometer line. There are some absolute differences. We believe EVE more than we believe C. C is now over 10 years old. We've been flying rockets to calibrate it, but there's a lot of degradation that we're correcting. EVE is new. We're also flying rockets to calibrate it, and we are also working on calibration. But it's fairly good agreement, and the variability within, like, over time is the same in terms of percentage as opposed to the absolute value. Here's a C spectrum overplotted with an EVE spectrum, and you can see they're very similar. There are some differences, especially around 304, where C has some scattered light that we're not correcting properly. The EVE instrument is giving better data there. EVE is much higher spectral resolution than EVE, and so we get all those details of lines, not down to the synthetic spectrum that Rodney had that showed lots and lots of lines, but we show quite a few of them. Now this is a movie of a flare from EVE. The top panel, it'll run again. The top panel is the GOES X-rays, the 1 to 8 and 1/2 to 4 angstrom. And the bottom, or this is a movie from SDO AIA of an active region as it flares. And you can see the complicated magnetic structure when the flare goes off. This bottom plot is EVE data, but it's the difference data. It's the data at the point in time that this red line is representing, minus the pre-flare spectrum. So it's just the change, the enhancement due to the flare. And you can see that pre-flare to post-flare and during the flare, there are lines that pop up that didn't exist in the pre-flare spectrum. This is just a small wavelength range from 8 to 15 nanometers. This is true over a much larger span of the spectrum. EVE also shows that flares are complicated. The mantra in solar physics is every flare is different. And it's really true, especially in the EUV. These are 3 different flares that are roughly the same magnitude. They're mid-C class flares. What I've plotted is a time series through each flare, and each color represents a different wavelength. And it's the same wavelengths in the 3 panels. And you can see that even though these 3 flares are roughly the same size as indicated by the X-rays, the spectral and temporal evolution is very different for each one of these. So you really need to be looking in the EUV to see what's going on in the EUV. We also discovered with EVE that some flares have what we're calling a late phase at some wavelengths, where after maybe 30 minutes to an hour or more after the flare, there's a secondary peak that at those wavelengths can contain more energy than the main peak of the flare. And that's usually not captured in any of the proxy models, even the FISM proxy model. So what's the future for EUV? So the timed prime mission ended in 2004, but we're still going. We don't have any money. We're still just processing our data. Our computers die and we fix them with duct tape and stuff. But we put in for an extended mission. We might get a little bit of money to buy new computers, and that's about it. But we're still going. SDO's prime mission is 5 years, until 2015. It's working great. There's no reason to expect it won't last longer than that. We designed it to last for 10 years. So hopefully we'll get through to 2020 at least. The current series of GOES satellites, the NO and P satellites, have for the first time EUV instruments. They're broadband measurements, and they've been measuring since 2009. The next generation of GOES, which will launch as early as possible, would be 2015. We're just building these instruments now, has a new kind of EUV sensor. And I'll quickly, very quickly, tell you about those. The concept is to use all our knowledge from EVE and timed, and instead of measuring the full spectrum, just measure certain wavelengths that are indicative of the different temperature regions in the solar atmosphere that vary differently, and then using empirical models based on proxies that are within the EUV itself, generate the full spectrum. So GOES-R and beyond will be measuring these different wavelength ranges within the EUV, and importantly, the magnesium 2-core-to-wing ratio. And we'll be measuring all of this at a 30-second or better time cadence and producing a data product within a few seconds after the data comes down. So GOES has us covered. So to summarize all 3 of our talks, Phil showed us that the EUV irradiance matters. It's important to the upper atmosphere, to all different aspects of the state of the upper atmosphere, ionization and density and temperature and composition even. The EUV is complicated. Rodney and I have shown a lot of information that it's really complicated. It depends on time and wavelength, and a single daily proxy, no matter what you use, is just not enough to capture what's going on in the EUV. EVE is helping us better understand our irradiance variability, and GOES is building on that knowledge, and will continue EUV monitoring into the foreseeable future. Thank you.